Welcome to this video. In this video, I wanted to look at deriving an expression and then actually the size at which a planet becomes spherical. So there is a size or a point where a planet will become spherical instead of more potato shaped like smaller asteroids or even smaller moons around some planets. So we're going to have a look at what point that actually occurs at and derive this expression to find out how we can then calculate it. So probably the first thing to really mention actually is one of the definitions of a planet. So the International Astronomical Union has a few definitions of a planet. Now one of those is that it has sufficient mass to assume hydrostatic equilibrium. Basically means it's going to assume a spherical shape. So all of the planets are spherical, and other objects like asteroids, some moons are not spherical. However, there are objects which are not planets which can be spherical, which is why this is just one of the definitions of a planet. They need to kind of hit all of those as well. So yeah, this does include some dwarf planets. So Pluto is one, for example. It's not a planet, but it is spherical. Some minor planets in the asteroid belt are spherical. These are kind of at the limit of becoming spherical. So Sirius is actually right there at the point where it would start to become spherical. Any smaller really, and it wouldn't be. So what is hydrostatic equilibrium? Well, this is where the inward gravitational forces that are trying to collapse the object are balanced by basically a pressure gradient, or this an outward pressure which balances against gravitational forces. So it is in equilibrium basically. So it's not collapsing, it's not expanding, it's kind of staying the same shape, or same size, I should say. So the first thing we need to do to work towards finding an expression for this is to consider a slab inside the actual planet. So we've got a slab, it's going to have some thickness, delta R. It's located inside the planet at some radial distance from the center of R. So we've got this small slab that has a small thickness of delta R. Now, the material closer to the center than the slab itself is going to exert a gravitational force on the slab. The material further away, we're going to assume, does not contribute a net gravitational force on it. So it's only the material inside that radius of where that slab is that is going to contribute to a net gravitational force. So we then have pressure acting on it as well. So there's going to be pressure from the material that's going to be underneath the slab. That will be basically pushing upwards. You've then got material above the slab which will be pushing downwards. Now, if the slab is at equilibrium, then the gravitational force must be slightly greater than the pressure above the slab. So we're assuming that it's in equilibrium, it's not moving anywhere, and that means that then this gravitational force is just slightly more than the pressure above the slab. Now, what that tells us also is that the pressure must increase with increasing depth. Otherwise, the planet would collapse. So that's one of the key things then, is that the pressure increases with increasing depth towards the center. Now we need to find an equation which then relates the pressure and the density. So we've got this slab which has a thickness of delta R. It's at some distance R from the center, and it has an area A. Now some things we're going to assume is that the planet is a perfect sphere. If that's the case, then the density and the pressure only depend on R. So we're assuming that it's going to be a perfect sphere. Now, the volume of the slab can be given as A delta R, so that's the area times its thickness, that's the volume, and we can then write its mass as the density times the volume. So the density times the area times the thickness delta R. And then we can also write the gravitational force acting on that slab from the material below, which is written at the bottom there. So the left hand part of that is the gravitational constant times the mass inside the radius of where the slab is, so less than R, times the mass of the slab over the distance from the center R squared. but we can actually replace the mass of the slab and put it in terms of the area, density, and the thickness instead. So we've removed the mass of the slab out and put it in terms of density instead, actually, an area. Now, the pressure below the slab, so the pressure of the material or from the material below the slab, is going to exert an upward gravitational force, which is then going to be equal to your gravitational force. And this is times the area. So the force acting on it from the pressures is the pressure times the area at that distance r. Basically, that's that first part there in the green. We then also got an additional part, which is a downward force from the pressure of the material above the slab. So the material above the slab is acting downwards. So we see that that's going to be a negative force acting on it compared to the one in the other direction. We then also got the gravitational force acting on it next to that. But again, we're assuming that it's in equilibrium. So the forces must cancel each other out. So all of those together should equal 0. Now, what we can then do is we can basically divide by A, and we can then actually rewrite that as the difference in pressure across the slab. So we can write that as delta P, which is like the change of pressure across the thickness of the slab. So we can then rewrite it at that bottom like that instead. Also, we're going to equate the change in pressure as well as the actual gravitational force. So we've got that expression at the bottom there for the change in pressure. Now what we can then do is if we divide by the delta R, which is your thickness of the slab, so the change or the slight change in radius you're going across the slab, we can then write it as delta P over delta R, but we can then also actually write that in the form of a differential equation instead, so we can write it as dP dr, and we get the bottom equation there. Now, what that then gives us is this is our basic equation for hydrostatic equilibrium of a sphere. So this is essentially the pressure gradient, which is then going to equal the gravitational force. So as you go to different locations, radial locations in this sphere, then the pressure should then match the gravitational force. So the next step really is to look at using a small shell, basically. So we can assume that the planet is composed of many very thin shells, and that's going to help us then get to the next part that we actually need. So each shell is going to have a thickness of delta R, same again as what the slab has. So we've got delta R, thickness of our shell. The sum of the mass of all of the shells within some radius r is then going to be the mass at less than radius r. So that's the same thing basically. So they should all add up to the total mass essentially. Now the mass of a single shell can be given as 4 pi r squared times the density times delta r. But if the thickness of the shell tends to 0, then the sum of the masses of the shell becomes the following integral. So we can write it in an integral form here. Now, we're going to make some assumption about the density and how it depends on the radius. Now, we know that the density is going to change. Realistically, in the real world, the density is likely to get greater towards the center. Okay, but we need to make some assumption of that first. We're actually going to make some assumption that actually it doesn't really change. We're going to assume it to be constant and assume it to be independent. So this is a fairly simple assumption to make, but it's going to make things a lot simpler basically. This time round, we're not going to consider the density changing as a function of R, but we know in reality that is likely to be the case. So if that's the case, we can actually then exchange our mass. So we had an expression for the mass within some distance r from the center, and we can put that down here instead, and we can put it in our differential equation that we had for the hydrostatic equilibrium. So what we're going to do here is we're going to assume that the pressure at the surface is 0 and that the radius at the surface is rp. And we can then actually write this in the form of an integral. So we can then look at solving it. And we're going to integrate between
the surface and some distance r, and the pressure is going to be going from the maximum pressure to 0, basically. So we've now got this integral at the bottom. So if we actually integrate that, we should get the following solution. So we get this for the pressure. And what we should be able to see actually is when we go to the center, we're going to get a maximum pressure. And as we go to the outer surface, it goes to 0. So when your R squared becomes the same as RP, then you're going to get a pressure of 0. And the other way around, if R is 0, then you end up with the maximum pressure. So yeah, you can basically see here that the pressure rapidly increases with increasing depth, as we just mentioned. So you can see where your maximum pressure is going to be and where your minimum pressure is going to be as well. Now, real investigations of the Earth show that the density changes by about a factor of 3 from the surface to the center, whereas the pressure increases much more rapidly. So it's not too misleading, basically, to assume that the density doesn't change. So we can assume, or at least our assumption of the density not changing is not too bad. It's going to give us a good approximation. So the maximum pressure, then, we already know is going to occur at the center of the planet, and we can write it like this, basically. So what we've got here is the maximum pressure which occurs at the center. Now, the interesting thing that starts to happen here is even rock can behave like a liquid under high enough pressure. So it can lose its rigidity and it can behave more like a fluid. And this occurs at a critical pressure. So the central pressure in the planet and the critical pressure are going to be important things we need to know. So for Earth, the critical pressure is 10 to the 9 Newton meter squared, or newtons per meter squared, basically. And the pressure at the center of the Earth, the actual central pressure, using this approximation here, is 1.7 times 10 to the 11. So we can see that the pressure at the center is quite a way above the critical pressure. So that tells you straight away that certain parts internally of the Earth, at least, are going to behave more like a fluid or a liquid than like a rock. Now, there are two regions in a planet or a rocky planet like this that are going to behave differently. So there's like two regimes essentially. One is going to behave like a rock, which is the lithosphere. That is the outer part. So that's going to include like the crust and the upper mantle. And then part of it is the rock is going to behave more like a liquid. And this is the asthenosphere. I think I've pronounced that correctly. And that is the rest of the mantle and a bit further down, where it behaves more like a liquid and can flow essentially. So you've got these two regimes. Now, the lithosphere of the Earth is about 100 kilometers thick, while Mars is about 500 kilometers. So Mars has a much larger lithosphere, but it's also a much smaller planet as well. And this again includes the brittle crust and the upper part of the mantle. And then the other part that behaves more like a liquid is denser. It has it's a weaker layer below this other one, and it's in the mantle between about 100 and 410 kilometers for Earth. Mars is about 500 to just over 1,000 kilometers, and that's down to size and the differences in pressure. A smaller planet is not going to have such higher pressures inside, so depths can change and things like that. Now, there is an interesting consequence here, as we mentioned, because it behaves like a liquid. So some of this inside of the planet is going to behave like a liquid. It means it can flow. And it's going to flow throughout the planet, and it creates a shape with the least gravitational potential energy. So it's going to mold itself into the most favorable shape in presence of that gravitational potential energy. And that's a bit like water running down a hill, really. You've got a liquid there, and it wants to go to a position of lower gravitational energy. And it's the same thing when you've got a large planet like that. Once it starts behaving like a liquid, it's going to then shape itself like a sphere. So what you can do then is you can work out what point this occurs at. Now we can do the calculation. We can already see straight away that there's going to be objects where internally their central pressure is always going to be less than the critical pressure. So the entire body will behave like a rock. Therefore, you're not going to get a spherical shape. So asteroids, minor planets, they're going to have internal pressures that are not greater than this critical pressure. And again, what you can do, if you assume a density of rock of about 5,000 kilograms per cubic meter, you can work out what that radius occurs at. And it's around about 535 kilometers that this occurs at, a radius at least. However, Ceres has a radius which is slightly less than this. This has been measured to 475. So we've done a fairly rough approximation here, but it's fairly close. And Ceres is pretty much going to be at the limit of that. And it could be that the density for Ceres is not what we've used here, and the fact that the density changes as a function of r as well. But nonetheless, it gives us a rough idea, and Ceres is pretty much at the limit for being spherical. So thank you for watching, and if you enjoy, then check out some of the other videos.